introduction. Yes, it is really, to me, it's an honor to be here with such a STEAM conference and colleagues, professors, and so on. The aim of this conference is to cross the boundaries. So my talk is to see how we can apply the visualization in mathematics education. And first of all, I want to give some minutes for talking about Darvas, Georgi Darvas.
Maybe Simone, can you go on full screen?
Okay.
Yes.
Yes. Okay. Because he was a very important person to me, and last December he passed away, so it's a way to honor him, because he was, and a lot of people know him, maybe someone of this group. And now I and Johan, we are doing, we are working in the journal Symmetry and Culture and Science as an editor, and so we are working on this journal, prestigious journal, and we want to make a renovation in the editorial team. So if there's someone that want to join us, they are really, it's a good thing. So, and Paolo maybe is just was a reviewer for this journal. So, and last summer we had a beautiful time for the Symmetry Conference, Symmetry Festival in Pisa, and it was a great time, and it's more than 30 years that the journal is alive, so we are doing this with a great honor. So we skip for this short introduction to Gyuri, and we go forward to the topic. My abstract is about to the visualization, to explore numbers and see if it can be applied at school. You know that geometry is linked with the imagination, and visualization is a kind of a training to for the imagination. And this is my aim. And maybe with this visualization, we can think outside the box. So it's to take a lot of structures from other divergent mechanism of thoughts. The first in the artifact linked with the numbers is the Ishango bone, dating at 2000 BC, and it's okay. So this fibula, in this fibula, you see that we have a lot of notches, and with these notches, we can see that we have 3 rows of numbers. And the first row, we can see that the numbers can be grouped as 20 plus 1, 20 minus 1, 10 plus 1, 10 minus 1. The second row, the row B, there's only prime numbers from 10 to 20. And the row C seems to illustrate the method of duplication. Even if there are no really connection with a tool for calculation, we can skip in the next slide. We see that can be there's different theories about this tool as a calendar for lunar calendar and so on. But however, it's the first artifact linked with the numbers. So, and it's a big mystery why it's like this. And you can see that the prime numbers. The second artifact that we can see for sure the prime numbers is the Ring papyrus. And you see that there's a lot of tables, and these numbers are different forms for prime numbers and composite non-prime, obviously non-prime numbers. We see that and we pay attention to the first table that is the mother table for two terms. We can see that with these fractions with denominator prime numbers can be obtained from the summations and divisibility conditions of integers. So this is the real historical fact about the use of prime numbers. We skip from this age to how to visualize the whole numbers. If you see this, I want to start by a way to visualize the numbers. This is the number 1, number 2, 3, and so on. And you can see that when it's possible to group numbers subdivide these numbers, the numbers have as a factor. Or when it is not, we have a circle. So this can be a way to show to students, even if small students at the early stage of school, that we can factorization the numbers. And you see that the circles correspond, to prime numbers. And it's a way to see numbers in a dynamic way. We move on, and you see that all we know what prime numbers are, but there's why we do care. We do care because they are like building blocks for all numbers. So there's this fundamental theorem of arithmetic, and we can see that every integer can be written as a product of primes. So this is the link with the visualization that we saw before, and we can see that 140 can be divided in 7 pentagons of where at vertices we have 2 times 2 dots. And we can have 7 pentagons, or we can have 35 4 dots. So but anyway, this is the unique factorization, and this is a link to Euclid. So these prime numbers are like a genetic code, is like building blocks of the life of numbers. And here you can see that we can build like a city of numbers, and each number is like a tower, and each tower has different building blocks. If we go further, we can see that these building blocks, for example, we can build the number 84. The number 84 is 2 times 2 times 3 times 7. So this is the building block, and we can see like a tower or like a circle. And you see that 84 can be divided in 2 times 42, and 42 is composed by 2 times 21, and 21 can be decomposed by 3 times 7. And the color are very important. Is very important because you can see that 84 has 4 can be factorized in 4 prime numbers. The form of we can use bricks to form numbers, and we can see if we have 7 bricks, we cannot build a rectangle other than that to have only 1 line. So this is a way to test if the number is building a rectangle, if the number is prime or not. So this is a kind a game to test a prime number. So and the rectangle is another way to building a rectangle, is another way to show the division theorem. If we can build a rectangle, we have a remainder of the division is 0. Otherwise, is not 0, so is not perfect division. Like 100 you can't have build a rectangle because you can see that there's 7 rows of 14 bricks, or 14 rows of 7 bricks, with 2 bricks that is not in the outside, that is outside. This type of building a rectangle can show the to find the GCD, to the greatest common divisor of 2 integers a, b, because we, for example, we want to find the greatest common divisor between 98 and 21, that is 7. We can see that we can have a rectangle with width and 98 and age 21. We can break in 4 squares, 21 times 21, and so that we can, and we can see that 4 times 21, we have 21 of 14, that is the remainder. Now we can build a 1 square 14 times 14 and so on and so forth. So we can see that at the end, the smallest square, non-zero, is the highest common factor of the two starting numbers. So this is a game, and it's a visual. So you can see that maybe they and this type of algorithm is not taught anymore at high school, and it's really, really depressing. If we go further with the prime numbers, we can see that after Egyptians in Greek, Eratosthenes invented this sieve to find all prime numbers. If we list all numbers from 1 to 100 and in columns, we can erase all factor by 2 and all factors by 3, all factors by 5, and so on and so forth. And we can see that the remainder are all prime numbers. And we can count how many prime numbers we have from 1 to 100, and we have 25. If we go further and you see from 101 and 110, we have 4 prime numbers more. A modern sieve can be, we can see another type of visualization of these to see prime numbers. This I can show in internet, and this is by Jason Davis. If I click, I can see that these semicircles are the factorization, the factor of 1. If I see this is a factor by 1, a factor by 2, and so on and so forth. But first, see the prime numbers only in the prime numbers, only two circles, 2 curves have been intersected. So this is a really cool way of seeing prime numbers. I go back to the presentation. Counting primes. All we know, this is really classic, how many primes are there. So if we list all prime numbers that we saw from 1 to 110, we see that there are 29. But Euclid proved that there are infinitely many primes. And he proved. And his proof is really cool because it's very simple and use a contradiction. If we suppose that there is that there aren't infinitely many primes, we can see that there's the largest prime P. If we multiply all those primes together and add 1, which primer we find? Euclid said that we find a number that can be divided by 2 because we have a remainder of 1, and we find a number that can be divided by 3 because we have a remainder of 1, and so on and so forth. So it's a different between all primes that were listed before. So this is the contradiction, because we have another prime or another number. So we at the school, we can see that we can try to have fun and see how many pairs of primes that are different by 2. So we take a punch card stencil that are 2 holes, and we can move this punch card stencil and see if the couple are primes of numbers. And you see that 1, 3 is not, 4, 6 is not, and the couple 2, 4 either, but we have a 3, 5, and 5 and 7. So we can see that we have a lot of couples of primes that is that differing by 2, and there's this conjecture that there are infinitely many primes pairs P and P plus 2. If we go further, we can see that there's another twin prime conjecture between that 2 primes that are different by 4, and so on by 6, and by 10. Oh, so this is a twin prime conjecture, are very, very simple to state, but very, very difficult to prove. If we try to prove it with the Euclid attempt that we did before to prove that there are infinitely primes, we can take 3 primes and we multiply together, and we add 1 or make -1, we obtain 29 and 31. And this is the couple is twin primes. But if we go further and we multiply together 2, 3, 5, 7 with +1 and -1, we obtain 209. But unfortunately, this is not a prime, because Euclid said that we obtain a number that is not divided by all the prime factor that we multiply together. But he didn't say that we find a prime number. And today, this James Maynard, Terence Tao, Yitang Zhang made a lot of progress about to prove this conjecture. And but only Yitang Zhang found a very astonishing result, a theorem that said that there are infinitely many pairs of primes that are different by almost 70 million. And so what? But it's very impressive, because we concentrate to close the gap and make this number smaller, so that we can find a result for attacking this conjecture. If we see this number and we make a module 6, meaning that we have 6 rows, and we write the numbers in this way, we have another result that we see that the line with starting by 4, starting by 6, there aren't any prime numbers, and only in the line of starting by 2, there's only that 2, and as the same and the 3. We see that only in the first and in the fifth rows we have prime numbers. So this is a very good result that every twins prime, except for 3 and 5, is one more or one less than a multiple of 6. So we can see that are the form of 6 times n plus minus 1. So this is a really, really cool, and we can, two students can see this result. Another way of looking at prime numbers, we divided all numbers in 9 sectors. And we see that every sector is all numbers, the modulo 9. So if we move forward, we can see that in the yellow sectors there are no prime numbers, and we circle the all numbers, prime numbers, and moving forward, we can see that all prime numbers that end in with the 1, we can color by pink, and so on, that end in 3, we can color by blue line. And we see that it forms a spiral. Moving on, we can see that we can join primes in the different sector, and we see that we have this arc like 7, 17, 13, 23, and these numbers are different by 10. We can move on to see with the arc of 20. If we move on, we can see that all numbers make this arc, and the interval of prime numbers are 10 or 20. This is the basic intervals, but the intervals of 13 can be like example 29, 59, we can color by green. And so is a multiple of these basic intervals. So this is really cool, and maybe it's a way to look at numbers. So I think that for students can give a creative way to look at prime numbers. We skip to see another type of visualization now is rational numbers in education. If we see, this is the Lissajous machine that two twinning forks is to see the figures that can be obtained by this machine, and we can see that we can have the different frequency, and we obtain all of these pictures, and how we can see these all figures with the numbers. With I made a GeoGebra machine. Is a file in GeoGebra. If we have two circles and I can move the numbers in numerator and denominator, maybe we can see 4/3. It means that the circle has the frequency of 4 and the frequency of 3. 3 is the blue one and 4 is the red one. So if I animate, we form this Lissajous curve. And we see that in the meantime, the point red make four turns instead of the blue one make 3 turns. If I change make the same 2 and 2, now we see that the animation can be see as a circle because the frequency is the same. So it's a cool way of looking at rational numbers. Okay, we move on with sorry, I need to skip from one. Magic squares. Magic squares is very old squares. That is schematic 3×3 magic squares, meaning that the sum of numbers in rows and column and in diagonal is the same. And we see that is represented in a lot of art, like Melancholia of Dürer. We see that is this is a magic square 4×4. And it is here we see that this is the date when it was made by Dürer. So we see another representation of a magic square in Antonio Gaudí, Sagrada Familia. But my research was to see how it can be visualized a simple magic square with this line or color, meaning that every number is depicted by a different color. And two children is so that every children has this magic square colored that can be applied to the solution of the magic square and see all symmetries for the 8th solution of magic square 3×3. We applied in for the children, and they saw all symmetry operation like rotation and flipping. We had a great result. This is because they could find the identity operation, rotation, flipping, and they had a lot of difficulties in making the flipping in the diagonal. But the astonishing result is that the rotation is a transformation that they can make easily than reflections. But in general, at school, the reflection is the first operation that they made. This is a way to see all a Cayley table of squares using magic squares symmetries. And we see that this magic, this is table is divided in four, and the configuration, we can see that there are four configuration, two rotation and flip. So that it can be divided in four quadrants. So thank you all for your kind attention.